So, hey guys, today's topic is text vectorizations and bag of words, including TF, ITF. So, you can use all the amazing words you want, like spectacular, thrilling, dramatic. But what does your dog hear? Just sounds right. So, it does not understand the meaning behind these words. So, machine learning ML models are exactly the same. So they are incredibly powerful at math, but they do not speak English, so they don't understand words. So their language is basically the numbers. So the fundamental challenge is like, how do we translate human language into mathematical language of computers? So this translation process is called text vectorization. So a vector is just a fancy word for a list of numbers. Our entire goal today is to learn how to turn a sentence into a list of numbers that an AI can understand. So, the preparation, that is the pre processing, that is basically cleaning the text. So, before we can translate, we have to clean up our sentences, just like a chef that prepares ingredients before cooking. So, let's look at the preparation, that means the cleaning the text section on the page. First would be the lowercasing. So, first we make everything lowercase because to a computer, the with the capital T and the with the small t are two different words, but lowercasing ensures that they are treated as the same. So that's the main agenda of lowercasing the words, so that they can become the same and they can treat it as the same. Removing punctuations, because now we strip out all the punctuations, commas, periods, exclamation marks, because they don't usually add much meaning, so we remove them to focus on the word themselves. So that is the primary reason. Because of that, we are doing, like, we are basically removing the punctuation. Tokenization, so this is the key step. So this is basically splitting the sentences into the individual words. So we tokenize a sentence, which is simple way of saying that we chop it up into a list of individual words or tokens, and removing the stop words. So that is basically, finally, this is very important because we remove stop words, because these are the most common boring words in a language, like is, the, in, it. So they are like the grammatical glue, like holding sentences together, but they carry very little unique meaning. So by removing them, we help the AI focus on the words that they matter. So for this, can we have the answer? Because the same question we did in the last session as well, so I think many of you know the answer. Can I have the answers in the chat box? Yes, that is correct. So it will be rocket sky. So basically, it is removing the stop words that is in the. So this will be, so it is just putting the commas. So now we'll see the bag of words. That is the simplest and most intuitive way to turn the words into numbers. So imagine if you take a sentence like, this cat sat on the mat, and you throw all the words into a grocery bag. So you ignore the order, right? The grammar and everything. So now to describe what is in the bag, you just count the contents. So, like, you would have two those, one cat, one sat, and so on. So that's it. So that's the bag of words model. So you lose the sentence structure, but you know now that you have a numerical count of what was inside. So basically, the bag of words model creates a vocabulary of all the unique words across a collection of documents. So it then represents each document as a vector where each element in the vector corresponds to a word in the vocabulary, and the value is the count of how many that word has appeared in the document. So can we have the example so you can see and like give the answers? Okay, for sentence 1 it is like that, but for sentence 2. Okay, so as you can see in this sentence, one apple is there, so it is one. Zero banana, so it's zero. One fruit, so one. And in this, as you can see, one apple is there, one banana is there. That's why it is, and two fruits are there, so that is why it will be two. So, like, basically, so by exporting from the skit, we import like count vectorizer, and the corpus is there. So for like basically the sentences, then we create an instance of the count vectorizer, so it basically handles all the cleaning, tokenizing, and counting automatically. And now we fit the vectorizer to the corpus to learn the vocabulary, and then transform the corpus into a document term matrix. So this is done by this. And about the like show the vocabulary that it learned in the alphabetical order is being by this, and show the resulting numerical matrix, that is the bag of words. So each row is a sentence, right, and each column is a word from the vocabulary. So that is how the print statement is being done, and it comes like this. And as we have discussed, so the thing is that there's a fit transform. So this is basically, this command is a two-step process, because the fit part scans all our sentences and then build the master vocabulary list, and the transform part then goes through each sentences and does the counting. And that has been done. So now the vocabulary for this, like, and the result for this code would be like 10110, because it corresponds to our first sentences. That is like, because it has one amazing, one plot, one spectacular, and zero weak. So we have just successfully vectorized our text. This is just a simple one. So now we will see the term frequency. So the formula for term frequency is like, I'm sharing it in the chat box. So let's break down its components. So TF is something that is term frequency. So the term frequency measures how frequently a term appears in a document. So it's the ratio of the number of times a term appears in a document to the total number of terms in that document. So this normalization is done to prevent a bias towards longer documents. And as you can see, the formula is TF, that is T comma D is equal to number of times term T appear signed document D divided by total number of term signed document D. So this, for example, if the word apple appears 5 times in a document of 100 words, then the term frequency for apple would be 5 divided by 100, that is 0.05. So that is how something like the term frequency is calculated. And like idf is something inverse document frequency. So this is something like it measures how important a term is. So while computing tf, all the terms are considered equally important, but however certain terms, like as we have seen in the stoppers, that would include is, of, and that, the, so they might appear a lot of times because they have a little importance. So, thus, we need to weigh down the frequent terms while scaling up the rare ones. So, the formula for, I'll share the formula for, wait a second. I'm not able to share it. So, yes, this is the formula of inverse document frequency. So, for example, if we consider a corpus of 10,000 documents, and if the word apple appears in 300 of these documents, so the idea for apple would be like log. 10,000 divided by 300. So that would be, wait, let me check. So that would be approx like 1.52. So this logarithm is used to dampen the effect of high document frequencies. So by multiplying these values, that is TF and IDF, you get the TF IDF score of a term in a document. And a high TF IDF score is reached by a high frequency, like high term frequency that is in the given document, and a low document frequency of the term in the whole collection of documents. So the way hence have to like tend to filter out the common words. So now we'll see. So as you can see, the word majestic and horse would get the highest scores because they are frequent in the sentence A, TF is high, but completely absent from the B, so making their IDF high. And the word would like queen would also get the highest score because it is the only word unique to sentence B. The word arrive appears in both the sentences, so its IDF score would be lower, making it less important according to the TF IDF. So now we will see the code part. So the best part is that it is almost identical to what we just learned. So instead of count vectorizer, we will now import the TF-IDF vectorizer. But from here, the process is the same because we create the vectorizer and we fit transform the corpus. So the library handles all the complex math for us. So now, so over here, as you can see, like the process words are a truly great, amazing flame. So the like as amazing is appearing one, flame is also appearing once, great is also appearing once, truly is also appearing once. And TF-IDF vector import, that is basically the importance score that is being calculated. So as you can see, for amazing 0.423 is the value, as best has not appeared, so it is 0. Boring is also 0. Film is 0.322. Great is also 0.322. So now we'll see other sentence. For this, as you can see, this code has differed. So, like the word spectacular is just not in the background corpus, right? So it's the T, like its TF-ITF score will be very high because showing that it is rare, and descriptive words are considered highly important over here. For this, as you can see, so like what it demonstrates is like great in film, each having a two in the bag of words vector, right? See, and the important score is also this. So let's check. So it is like a sentence full of common words. So like this sentence is already in the background corpus, right? The words plot, best, and part appear elsewhere. So their TF-IDF scores will be relatively low, showing how common words get penalized. So in this, like you can see, after pre-processing, almost all the words will be removed, leaving only movie and the film. So this powerfully illustrates the impact of the stop word removal. So is this a movie? So these all are the things that add less semantic value. So that is the reason they got tokenized, and like due to the stop word removal. Okay, now we'll see another example. So in this, like you can see, the words boring and terrible will get high TF-IDF scores, like assuming because boring is also rare, right? Showing that the model values show strong sentiment words, whether positive or negative. So, in this slide, the sentence shares the words great and masterpiece with the background text. But we can compare the TF-IDF scores of this share words to the more unique word, that is truly. So, okay, so this film was released in a theater. So as you can see, with the stop word, the was is removed in is also removed. Only three film release theater is there, and like it will both of these words will get a moderate TF-IDF score because likely lower than the strong opinion words like amazing and boring. As you can see, like this is a great experiment because if we add film to the every line in the background corpus, they will see the TF-IDF score for film that would drop to zero. Right. Okay, so over here, like we can see, like this shows how strong the sentiment words like amazing, incredible get high TF-IDF scores because they are the powerful clues. It also shows that the word appearing in the corpus already, that is camera and battery, get lower scores because they are less unique. And I change the corpus. So over here you can see like these highlights how the topic specific keywords like AI algorithm becomes important based as well because they are unique to the technology topic and do not appear in the sports or politics headlines, right? As you can see, that is the reason. Based algorithm, AI, tech. So, well, so this is tricky, right? Because the sentence contains keywords for both a feature, add feature, bug, that is like basically feature is like add feature and a bug that is fix error. So as you can see how it gives like it will show which words like the most TF-IDF considers the more important, like based on the rarity, right? See. So you can see over here, like this shows what happens when a sentence is composed of like almost entirely of common overlapping words, like because the butter, eggs, salt appear all in the background, right? In the corpus. So every word will get a relatively low TF-IDF score. So it shows that when no word is rare, no word is considered particularly important. So you can see like only new unique sentence is there. So the words this is and sentence are so common in the corpus that their TF-IDF scores will be almost zero, and new and unique will get high scores. So this is pretty much about it. So any questions? Oh, so sorry, I could not share it. Yes, I will share the notes now only to the team and they will share it to you. Whose mic is disabled?
Hello, ma'am. Ma'am,
Yes,
am I audible, ma'am?
yes,
Ma'am, I have few questions.
yes.
How does this text factorization help AI to understand the structure and meaning of language?
Of course, how can I help you?
So can you repeat your question,
Yeah,
please?
ma'am. Sure. How does this text factorization help AI understand the structure and meaning of language?
So like how does this text vectorization help AI to understand, right? The
Yeah,
scripture.
the structure.
So basically ML cannot understand the sentence, right? So that is why we are performing text vectorization.
Hmm.
So that is the primary agenda that I have explained in the first, like when I was introducing it, because ML cannot understand the sentences. So that is the primary reason we are like
How it is
reprocessing.
understanding the meaning of language?
Sorry.
How it is understanding meaning of language.
So basically, machine learning only understands numbers, right? That is
Mm,
binary, 0 and 1. So that is the primary reason that we are converting the sentences into numbers.
yeah, man.
Yes.
Can AI models learn their own factors automatically during training?
No, actually, we need to feed, like, of course, like, the thing is that first there is training set as well, right? So we
Yeah.
need to train them on specific tasks. Then after that, then it recognizes the pattern and itself, then it learns it. But first, we need to feed the data. That is basically the training set. So
Okay,
training
man.
should be done, right? At first, the machine learning model should get trained on some certain amount of data, then only it can learn on its own. So the accuracy and everything that needs to be calculated, and post that it will be like successful. So like, yeah, Vishal has asked one question. Okay, sure, will. So okay, I will share the formula. So the formula for like basically the goal of TF-IDF is to calculate the score that reflects how important a word is to a specific document within a collection of documents. And the formula is there, like I've shared it. So term frequency is something like, so that is the word comma document. So number of the times the word appears in the document divided by total numbers of the words in the document. So, like for example, our sentence is the movie made $100 million. Okay, so after removing the stop words, like the we are left with the five words that would be movie made 100 million comma dollars. So the total number of words would be five, right? Okay. So now we need to calculate the TF for the word 100. So like the formula is there. So as you can see, TF word comma document is equal to number of times the word appears in the document divided by total words of, like total number of words in the document. So in this sentence, like after doing the stop word removal, the total number of words is five, right? So and like 100 is appeared once, so it will be 1 by 5, that is 0.2. Now we'll calculate the TL for the word movie. It will be the same because movie also appear once, so it will be 0.2. Now we'll check the IDF, that is inverse document frequency. And like this measures how rare a word is across all the documents in your collection, that is the corpus. So let's imagine we have 10,000 documents, example like news or articles, and the word movie is very common and it appears like in 5,000 of these documents. Okay, so the number 100 is much rarer and might only appear in 50 documents. For example, articles about age, money, or list. So that is there. So now we'll calculate the IDF for movie. Okay, so yeah, once again I'll repeat. So let's imagine our corpus has 10,000 documents. Okay, so for example, that would be news or articles. Then the word movie is very common and it appears in almost like, we'll take for certain only like 5,000 of these documents for easy calculation. We are taking it. So the number 100 is much rarer and might only appear in 50 documents. For example, articles about money, list, or etc. So like idea for movie, like we'll calculate the idea for each word, that is the movie. So that would be like, as I've stated, that 10,000 corpus is there, and the movie appears almost in 5,000. So it should be log 2. And the value for this, like log 2, would be 0.3 almost. So now we need to put it all together, that is TF-IDF. So the collective formula for TF-IDF is term frequency into index, like inverse document frequency. So for the word movie, we have calculated inverse document frequency as well, and TF is also calculated for movie, right? So now we will calculate the TF-IDF score for movie. So that would be zero point 0.2 into 0.301. So that is 0.00, like 0.0602. Okay. So this is how the TF-IDF score is calculated. Yes, Vishal.
Um, I'm asking in the background
Sorry, your
process.
voice is cracking.
Hello, I'm audible.
No, 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 no. Come closer to the mic.
Hello,
Still not so clear. Like,
no, I'm audible.
yes, please.
I'm asking in that background process, what is the correction of n value? Like the three sentence you have been given. This is a sentence. This is another sentence. This is the final sentence. I am asking the n value.
Vishal, your voice is cracking. Can you type your query in the chat box if that's possible? Okay, so that is calculated by IDF is equal to log n by n. So the value of n is the total number of documents in the collection. So like for sentence, we can see like it also appears in sentence one, sentence two also, sentence three also. And let's assume like our sentence is also like in our sentence also the sentence is appearing. So in this case, small n is equal to 4. And for the IDF that is there, so 4 by 4 is equal to log 1 only. But for final, if we'll see the collection that is equal to n is equal to 1 only, because like only once the final word is appearing, right? So it will be 1 for IDF. Final would be 1, 4 by 1. So this is it for today, and this is how. And I will be sharing the documents like I have shared it. The support team will share it to you. So sorry, I forgot to share it that day. I think by tomorrow you will be getting the documents that I've used. Yes, that is right. Including the below sentence as well. So four is there, right? One, two, three, four. So that is why I've used four over there. Yes. Okay, then we'll conclude the today's session. The materials will be shared shortly.